This is the second part of video 271. We've been talking about total internal reflection and the critical angle. So let's do some examples. This example here says, what is the critical angle for a ray of light that goes from glass to air? So we have a boundary here between glass and air. And we learned that the critical angle is when you have your incident ray is big enough such that all of the light is reflected back into that medium. None of it goes through here into the air. So that is the angle that we have to find. We just defined the critical angle as theta c equals the inverse sine of n2 over n1. So all we have to do is plug those numbers in. N1 is going to be the glass, the incident angle here, and 2 is going to be the air. So we're going to take the inverse sine of 1 divided by 1.5. And when we do that, make sure that you're in degree mode in your calculator. We're going to get 41.8 degrees. So if you had mixed up the two indices in this equation here, if you try to take the inverse sine of 1.5, you'd get an error. So you know that N1, where the light is incoming from, always has to be bigger than N2 in order for total internal reflection to occur. Let's take a look at the next example. A small spotlight is mounted at the bottom of a 3-meter deep pool. What's the diameter of the circle inside which a duck swimming on the surface could see the bulb? So yes, there is a duck in a swimming pool. So we have a light bulb here. It's emitting light in all directions. And for these smaller angles of incidence here, over here, you've got some light going through. But over here, you've reached a critical angle where the light is reflected at 90 degrees. So any angle greater than that, the light is reflected back into the water. And if your duck is over here, then it's not going to see any of the light here. It's only going to see the light that is coming out of the water. So what this problem is really asking us to do, first of all, is find that critical angle, because that theta c here, which is the same on both sides here, is what's going to determine the size of this circle. So the critical angle is going to be equal to the inverse sine of n2 over n1. So n1 is going to be the water here, 1.3. N2 is going to be the air, 1. So plug in those two numbers, and we're going to get 48.7 degrees for this critical angle. Now what we need to do is use some geometry or trigonometry here to figure out the size of this circle. So what we can do, since we have the depth here of the water, we have this side right here, we can make a triangle here, like this. Triangle right here. And we have the critical angle which we just found. Let's solve for this side here. Let's call it R. Let's call it the radius. And we have H here is 3. So we have the angle, we have the opposite, and we have the adjacent. We know that the tangent of our angle, the tangent of this critical angle here, is opposite over adjacent. So it's going to be R divided by H. We can use this to solve for R. R is going to equal H multiplied by the tangent of our critical angle. So we can plug in 3 for the height here and multiply it by the tangent of 48.7 that we just found. And we're going to get 3.4 meters. That's the radius here. So I know this doesn't look like a circle, but the light here is coming out in all directions. So it's really making a circle here. And we just found the radius of that circle. So now if we're looking for the diameter of that circle, we can just multiply this radius times 2. Diameter equals 2 times the radius, which is going to be 6.8 meters. So that was an interesting application of total internal reflection, and realizing that the critical angle here is what is going to determine the size of the circle through which all of the light is going to exit the water. It's not going to exit at anything greater than this circle, because any greater angle you have total internal reflection. So I have one more question in this section. Your turn here. Based on this picture, we need to figure out what is true about these indices of refraction. So we have a boundary here between objects 1 and 2, and a boundary here, between medium 1 and 2, and an boundary here between medium 2 and 3. So it says that the laser beam, your light right here, undergoes 2 refractions and total internal reflection over here. So let's look at the refraction between medium 1 and 2. We always like to draw that normal line, perpendicular here. So this is the angle of incidence here, and this is the angle of refraction into medium 2. And what we have to figure out is the light bending toward or away from the normal. Hopefully you see that instead of going straight, the light bent away from the normal. Whenever the light bends away from the normal, that means that the speed of the light is faster, which means that it's going into a lower index. So this means that N2 is smaller than N1. And then let's look at the total internal reflection occurring. Total internal reflection only occurs when you're going from a bigger index to a smaller index. So that means that N2 must be greater than N3. So with those two things in mind, if N2 is greater than N3, but N1 is greater than N2, then that means that N1 must be greater than N3. So that is our answer for this one, and this concludes the videos on reflection and refraction.